So I did example 5.a.9. So the given is a thin homogeneous bar with a weight of 20 pounds is attached to a vertical shaft. It has a moment of 100 pounds per inch and is applied to the shaft when the bar is at rest. So what we're trying to find is the reaction forces of this right here. So OY and OX. So here's step one. We draw a free body diagram of it. So then we know that we're going to have our acceleration due to gravities in the middle of the bar. Then we're going to have OY and OX and then our moment. And we're in the I and J coordinate system. So step three, we'll write out our forces, which is just OX in the I direction, OY in the J direction. Step four, we do our accelerations as vectors. So AGX in the I direction and then AGY in the J direction. And then we have step five, which is the sum of the forces equals the mass times acceleration. So we set it up right there. And then step six, we go into our sum of the moments equation, which this right here is IG and then alpha, and then our sum of the moments is the moment plus OY times the distance from O to G. And then since we can't figure out everything that we need to know from this equation, we have to go to step 7, and we use one of our equations that we learned in chapter 2. And so from that, we get AGX is equal to 0. AGY is equal to negative alpha times the distance from O to G. And then from those, we can figure out using this equation over here that our OX is going to be 0. So it's not going to have a reaction in the X direction. So then solving for AGY to plug into this equation. But first we have to solve for alpha, which is done here. So alpha equals 16.53 rads per second. And then once we figure that out, we can just go ahead and plug it straight back into this equation right here to solve for AGY. And that AGY equals negative 49.539. And then to solve for OY, we take the mass, which we take the weight up here, and divide it by the gravitational acceleration, and then multiply that by our alpha, and we get OY is equal to negative 30.77 pounds.